right, so this mini lecture is going to take the ideas of wave speed that we talked about in our kind of introduction to waves mini lecture. So if you haven't done that, go back and get that information so you really have a good solid foundation for where wave speed comes from. And it's going to look at what influences wave speed. And then we're going to use an example of a waves on a string, which is a great example to start with. We start to play with these ideas of waves traveling, this energy traveling through a medium. And we're going to use those ideas to introduce how do we use this information to solve problems. All right, so we learned in our previous discussion of wave characteristics and properties of waves and descriptions of waves that the wave speed is related to the wavelength and the frequency of the wave. So the wavelength being how long that wave is, the frequency, how many cycles per second that wave is traveling. And we can appreciate that if I have two waves together, traveling along together, and one is bouncing along really quickly, and the other one's kind of more less frequent happening, that if they're both traveling together at the same velocity, then as I increase the frequency of the wave, my wavelength goes down. Or if I increase the wavelength, my frequency goes up. If I increase the wavelength, my frequency goes down. If I decrease the wavelength, my frequency goes up. That's what we talked about. But what dictates how fast those waves are traveling? Not how frequent they're going up and down, but how fast they're getting through, how fast that energy is moving through a medium. And you may have some experience with this already. If you, by any chance at home, have a Slinky, it's a great way to kind of play with this idea. And we find that if I have a really loose material, like you can even do this with like an elastic band or an elastic string. If I have a loose material, those waves tend to travel more slowly. If I have a really loose string and I try to flick it, the wave dies pretty quickly. There's a lot of energy lost, but it doesn't go up very much. If I tighten that string, pull on it really tight, and I flick it, that wave shoots down. We find that it's the medium itself that dictates wave speed. Now, why might that be the case? Remember, waves, what they are is an energy disturbance as it travels through the medium. So you can imagine if that medium is really loosey-goosey, that energy is going to be used to move sort of all of those particles, kind of moves them slowly. If that medium is really tightly bound, imagine like a liquid versus a solid, that energy can dissipate through that medium much more quickly. You might have had experience of this with sound waves. So sound is a wave. We're going to do a whole series of mini lectures, of course. There is a whole series of mini lectures on sound waves. But let's imagine sound being a wave. You're water skiing, and you're underneath the water, and you hear a boat underneath the water, that whiz of the engine, of the propeller. That sound's hitting your ears, and you pop up, and you look around because you think, oh my God, that boat's really close by. And you look around, and it's really far away, and you can hear the boat, but it sounds now so far away. Why did it sound so much closer underneath the water? Well, sound travels through air at a certain speed. When I move into water, a little bit tighter knit molecules, right? Energy can transfer through that much more quickly, and the sound gets to us from that far away boat much more quickly. If I move that sound into a solid, the sound travels even faster. So it's the medium itself that dictates the wave speed. All right? Every wave, whether high frequency, low frequency, large amplitude, small amplitude, every single wave travels through a medium at the same speed. If I change the medium, the speed changes. potentially, right, if it has a different medium makeup. The medium dictates the wave speed. All right. So let's look at the specific example of the medium of a wave on a string and see if we can even dive a little deeper. We can dive a little deeper into an example of how we use this now information, and can we understand wave speed even more? Can we use a different descriptor, including frequency and wavelength, to talk about how wave travels through a string? All right, so go back to that slinky example. If I had a really loose slinky and I flicked the end to make a wave, we would see the wave travel through. What do I need to do to that slinky to make the wave travel even faster? Well, what I do to that slinky is I pull it apart. I make it tighter. When I increase the tension, this capital T is tension, not period with the two tau, capital tau. When I increase the tension, I increase the wave speed. If you want to go back and kind of equate that to kind of molecules interacting, right? Air is loose, water's tighter, solids are even tighter molecularly. So I'm increasing that molecular tension. Not exactly the same, but it kind of gives you that visualization. So if I increase the tension, I increase the velocity of a wave. In addition, I can change the material itself, the string itself. Waves travel differently through nylon rope, or along, not through, but along nylon rope, than they do through that other kind of rope, cotton rope. All right, so the material itself plays a role. Similar to when we talked about how materials affected other things, like friction and with mu and springs with their spring constant. So the material itself and the property of the material, the property of the string, is what we call the linear density. Now, this is given as K. It's also given as mu. We use a lot of the same symbols in physics, but so you need to recognize what this particular relationship is. I'm going to use mu for our linear density, and that is, as a linear density, we know density, when we learned about fluids, is mass per volume. Linear density is mass per length, okay? So it's looking along the object, only in that single dimension. And as I increase the linear density, I decrease the speed. So as I make more material density, I decrease the speed. And what this gives rise to is an equation for waves on a string that's going to be very useful for us as we solve problems of different waves on a string. The velocity for a wave on a string is given by the square root of the tension over the linear density. Square root of the tension over the linear density. So this is one way dictated by the medium. Here's where it tells us this is how we define the velocity. The velocity then relates the frequency to the wavelength. So this is what determines the velocity. It's causal. And this then is a relationship based on that velocity. All right, so this is very important. So for waves on a string, spring, chain, we're going to kind of combine those into one. Our velocity is dictated by the tension over the linear density, or mu. That linear density, this is a property of the material. So it's different for different materials. All right? Okay. Velocity, wave speed, wave velocity, wave speed is dictated by the medium. That's your first take-home message. That wave speed for a string is dictated by the property of that string, the tension, and mu. But regardless, whether we're in air, water, on a string, in the inner ear, in our bones, in the inner ear, in the fluid, in our cochlea, that wave speed is dictated by the material itself. All right. Good job.